what should we do? Anytime we want to understand a unitary matrix, or any linear matrix, we want to understand its action on basis. This we have done multiple times, right? Whenever you wanted to create a circuit, you want to see how, if directly some structure emerges, we are lucky. Otherwise, the basic bare bone thing is to try it on basis, right? What is the basis here? Correct? Right? I shouldn't write K, okay? J, K, L. What will come here? You have the matrix in front of you. There has to be some coefficient, right? This is my basis vector. When I apply this, it will give me some linear combination of bases. What is the coefficient here? Tell me from here. Should be obvious. Sure. This is the lth column here. Yes. This is the JLth entry of this. You have been studying matrices for such a long time. Remember the intuition, right? What is this? This is telling me the action on state 0. This is telling the action on state 1, state 2, state J, WJK. Okay, JL, right? I won't use K because K is already taken. Correct? This is what we want to do in general. In this case, W will be I. Correct? Now, even though these are 0, 1, 2, 3, as Suyesh pointed out, on our computer we will write it as qubits, right? Finally, this circuit when I make, I am going to have J in a qubit representation. J is J1, J2. J1 is the least significant bit, J2 is the most significant bit. Correct? And then finally, some gates here, some gates, and here I want this state. Yes, no, right? This is the way. So then let's write it this in terms of L in binary, J in binary. Okay. So now let's take K equal to 2. How many choices are there for L? 4, right? 2 square, 4. So then correct? What are the coefficients here? What is the coefficient for 0, 0? Omega to the power j times, what is L? This is the binary representation of 0. So L is 0. What will I get here? Omega to the power? Again, this is what you have to do in research, try all these simple cases and hope some pattern emerges. So then, under F, 0 will go to, so what will this go to? If J is also 0, this is going to be, there is a unitary to make it normalized. I will have a so I have k equal to 2. Yes, thank you. Right? So we see actually that if you want to create equal superposition, we could apply Hadamard or we could apply QFT. We don't have circuit for QFT. It's much more complicated, but even QFT will give us equal superposition. Will it give us the same thing as Hadamard here? You can check no, because they are different things. And these are what? So this is what we want to get. So I have why is J multiplied by 1 here? Because this is 1. Why is J multiplied by 2 here? Because this is 2 here. Because it is 3. Right? Let's just write these 3's in terms of these. What is this? This is a binary, this is the number associated with binary string 0, 1. This is the number associated with binary string 1, 0. This is binary with 1, 1. This is completely fine. Correct? But what this does is allows me to move the amplitude according to this with the same thing. And this is the trick we even did while using the Hadamard transforms. So what we get is 0, 0, this part of the phase is coming because of this 0. This part of the phase is coming because of this 1. Everywhere this is true, right? If you want to write it, sorry, I should write like this. Right? So this part is actually associated with this part. This part is associated with this part. So I'm just distributing that phase to that part. Okay? But if I do this, what is this? Again, the same thing which we did when we did like this Hadamard, big Hadamard. This is actually pretty nice. I will give you a minute to think about it. You should be able to do this. Just in terms of omega. Don't worry about this. Is okay. Let me give you a hint. You don't need any quantum. This is high school math. Okay, 6th class math. That's why you are stuck. It's too simple. What is this? Sure. Now? This is great. You see how much it is simplified now. You just want to convert your J1 into this, J2 into this. This is the real magic in doing QFT actually. This class 6 formula, I don't know, class 6, class 8. This is the real magic which makes us do QFT. The simple realization that you can factorize and now you can do it in some sense qubit by qubit. We will do it. But are you okay with this? Is this okay? Now you see a hope? What is this? Okay, let's simplify. Let me not write the circuit now. This is minus 1 to the power j, right? So, okay. Let me simplify this. Sure. What is j? You have to write it in terms of binary J1, J2, right? J is 2J2 plus J1. Correct? What is this? J2 and J1 are numbers. Minus 1 to the power 2 J2 is useless. What is this? How do I convert J1 into this? Header word. Just apply header word on J1. You will create this. That's all, right? Now, this is slightly non-trivial. Done? Okay. Now, this is I to the power right? I square is minus 1, right? I can get this part of the phase by applying Hadamard on J2. How can I apply this phase? This is saying, so on J2, J1, this will create this phase. This is saying, depending on J1, put a phase of I, right? Look at this matrix, R, I don't know what I want to call it, R2. I. Correct? I want to apply this only if J1 is 1. Right? So what is this saying? Again, the phase will only be applied to one part. The phase will only be applied to one part. Right? So then, how do you apply this? Okay. Sorry, wait. Oh, sorry. This is a simple gate, right, which just applies phase of I when my qubit is 1. But this one, I only want to apply if J1 is 1. This will execute this. If you, okay, how will I do this? Let's say my J2 should move to this state. Control Z with control on J1. Now this is control R2 with control on J1. That's all. Right? And remember, what were we supposed to do on J1? We were supposed to apply Hadamard. Why didn't I apply Hadamard here? Because the control will change. So this order is actually important. Okay, and depending upon, the most significant and least significant bit, you can even, so generally in this case, the order will be opposite, but you know how to swap qubits. So that's okay, right? So this was the most significant bit which became least significant bit, but we can always swap that. That's okay. But the point is, we're going to create these, because of this factorization structure, we can create these qubit by qubit. That is why QFT is possible. Right? So in general, if K is 3, J, 2J, you will get 4J. You can check it, you can calculate it. Okay, for general K calculation is given in the notes, but this is what will happen. So for 2, is this clear? We wanted to get this state. This is very easy. This is just Hadamard on J1. This one is Hadamard on J2, and then I want to apply an extra phase of I if J1 is 1. So that's a control R2. Questions? So So you see that J1 goes here and J2 goes here. That's why I had swept. That's not a big thing. We know how to swap quantumly, right? If you don't remember 3 C naughts, do the swap. Question about the 2, otherwise I will show you 3. Very similar idea. From there you will get the idea for general. Let's try for k equal to 3. Probably things will become clearer. Same ideas. I will just keep repeating it. You can see in the notes how to do it for general k. So now I have J1, J2, J3 is my state. I want to convert it into this. Correct? Now, what happens? Let me look at this. What is this omega is what here? What is n? 8th root of unity, right? What is the 8th root of unity? E to the power 2 pi by 8 into 4. Which one did I take? J3. This is the state. This is my omega. This is my J, and this is 4 from there. Right? Now what happens? To 4J3, is it going to give us something? No, e to the power 2 pi I is 1, right? So anytime it is multiplied by an integer, nothing to do, right? So I will get, what state will I get? E to the power 2 pi I. This won't do anything, this won't anything. This is 0 plus this is just Hadamard, right? So now this is done. Do you want to do similar calculation here? Correct? Again, now which out of J1, J2, J3, which one can I ignore? J3 is useless. 8 times J3, 8 by 8, 1. Correct? How will I get this? Hadamard on J2. Here, control R2. So now this, how many phases will you break it down to? All three, right? Because what will come here? Okay, tell me all these phases. This is math. There is nothing quantum. You have j e to the 2 pi by 8 4j3 plus 2j2 plus j1, right? So minus 1 to the power I to the power remember 1 qubit gates are there for us. So then this one will appear by control on I to the power j2. So control on what should come here? What again did I reverse? No, yeah, I think I should. Yeah, so you have to remember in my notes, I might have exchanged the most significant bits and least significant bits, but the idea is the same. Once you have the factorization, then now what do I do with J2? So now first I have to do this, right? Because it has control from both. I can't touch J2 and J1 before I do this. So what do I do with J2? This takes care of this one. What I want to emphasize is that this is a nice exercise in creating a circuit, but more importantly, it tells us that we can perform QFT on Z to the power k. And now, whatever you were planning in the beginning, we wanted to see if there is some natural problem for Z to whole to the power k. Now we will see that there are indeed very natural problems on this group. Once we can do QFT on this, then we can do the finding subgroup kind of a thing. Remember, what was the idea of a Fourier transform? You had a subgroup, led to a partition. You tell me partition, I can tell you the subgroup. You do the same thing here and we will solve factoring. Okay? And this was the essential idea for Peter Shor. Once he saw Simons, he saw that Fourier transform on Z2 whole to the power k was possible. And from previous work, he knew that if he could do Fourier transform on Z2 to the power k, he will solve that. Okay, so this is where now we are in the right position to now move towards Shor's algorithm. Simon tells us Fourier transform is helpful. We want to find out if there are other groups where Fourier transform can be done. We just saw Fourier transform on Z2 to the power k can also be done. And we will convert our factoring problem into this. What do you think? Should it be CR3 or CCR R3? Does it depend on J2? This phase of root I? It does not, right? This phase I only have to apply if J1 is 1. It has nothing to do with J2. We are applying this and I am converting J3 into this. So this one will be achieved by Hedderwood. Here, using J2, I have to put a phase of I. This is control R2 with control on J2. This one is just control on J1. The phase of root I only depends on J1. It does not depend on J2. And yes, I can tell you that this is the circuit for QFT. And then I can tell you that we can solve Shor's algorithm. But I would still say our understanding will not be complete if we don't understand this basic connection between all these algorithms, which is coming because of Fourier transform or group theory. That's why I think it is really important that you look at that video lecture which I have made or the notes and understand that there is a deep connection between these algorithms. They did not come out of, the box. Shor just slept and woke up morning, QFT. No. Because he had Simon's algorithm, he knew that Fourier transform could be useful. The point was, can he do QFT? Can he do Fourier transform on the different group? And once you have that, it's not that difficult. I think the punchline here was that sixth standard factorization, right? Remember factorized? Then we can do it. Okay. And then what we will see now is that factoring is this problem called order finding over group, and order finding is this subgroup partition problem on a different group. That's the essential idea. Okay, so on 24th I will finish it. Then we will go to this amplitude amplification kind of algorithms, which are another different, very nice beast. And good thing is that even a few things in QFT, Simon is not clear, you can forget all about them. You remember the reflections, you remember Elitzer-Wedman, you remember Max Zender. We will just take a very, very different route. So even if things are not clear to you after mid-sim, you can start afresh after the 24th, then 29th, from 29th lecture. So we'll see an application of this, which is Shor's algorithm, and then we will move forward with, very basic quantum circuit knowledge. Okay, have fun.